Now we know how to describe motion in terms of position and velocity. What happens if velocity starts to change? Well, in physics we've got a term for changing velocity and we call it acceleration. Now acceleration is a word that's used in everyday language and it almost always means to speed up. When you accelerate, you think you're going to speed up. In physics that's not quite what we mean. In physics, any change in velocity is an acceleration. And that leads to an interesting idea. If you're sitting in your car, you've got a choice of accelerators. You can look down on the floor and push on the pedal on the rightmost side of the car, and that will speed you up. That's an acceleration. We often call that pedal the accelerator. Right beside that pedal is another one you can push. You push on that pedal and the brakes are applied and you slow down. In physics, that's an acceleration. So your brake can accelerate you. There's a large round thing in front of you normally. You can turn that. That's the steering wheel. That will change your direction. In physics, that's an acceleration. So you've got a large round accelerator in front of you as well. So it's important to realise that acceleration in physics doesn't mean speeding up, it means a change in velocity. We write that change in velocity as acceleration, which is a symbol A, and it's a vector, equals the change in velocity, delta V. Remember delta here, the triangle, is telling us the change in a quantity divided by delta t. And just to remind you again, that's going to be the final velocity minus the initial velocity, again divided by delta t. So we might imagine our car here had some initial velocity, and maybe, for example, you did step on the rightmost pedal and you made it a bit faster to give it a larger final velocity. Now this is an average again, so we better go and write average under here. It's the average over some time, delta t. What if we want the instantaneous acceleration? Well, we do the same thing we did with velocity in the previous topic. We take the limit as our time interval becomes vanishingly small of the change in velocity divided by change in time. That, again, if you know your calculus, for those of you who like mathematics, that is the derivative, the time derivative of your velocity. In either case, this is going to be now the slope of a velocity versus time graph. And the units we're going to measure it in will be the units of velocity, meters per second, divided by the units of time, which is second, which ends up with being meters per second squared. So that's what acceleration means for us, but importantly, there's something acceleration does not tell us, and that is acceleration doesn't tell us the direction that we're moving in. Let's look at a quick example here with our car again. Imagine we're starting off with some initial velocity here, and we speed up. We go to a larger velocity at some later time. Remember now, our change in velocity, our final minus our initial, will now point in that direction, the direction we were travelling in, because we got faster and faster. Our velocity increased in that direction. So that means that our acceleration, which points in the direction of the change in velocity, will also point in that direction. What if we do something different though? Our car starts off with an initial velocity in that direction, and we slow down and end up with a smaller velocity at some later time. Now, our change in velocity will actually point opposite to the direction we're travelling. Because we're slowing down, our change in velocity actually points backwards. And that means that our acceleration will also point in that direction. Our acceleration now points opposite to the direction we're travelling. So acceleration doesn't tell you the direction you're travelling. If it's in the same direction as your motion, you'll speed up. If it's in the opposite direction, you'll slow down. What about if you actually change direction? Let's have a look at the problem now when we're not going to restrict ourselves to being in one dimension. Let's turn a corner. So in this example here, our car starts off travelling in one direction with some initial velocity. And let's imagine it doesn't change its speed, but it changes its direction. So now I'm going to draw an arrow that's hopefully about the same size as my first one, but in a different direction. You can see there that the car's turned a corner. Remember, my change in velocity is going to be equal to the final minus the initial. How do I do that with vectors? Well, I start with my final velocity. Here it is here, it's an arrow pointing downwards. And if I want to subtract off the initial velocity, I've got to draw the vector minus the initial velocity. The initial velocity was off to the right, so I'll draw minus the initial velocity off to the left. So there's now minus the initial velocity. And to add them together, I simply draw a line from the start of the first one to the end of the last one. And that line there is now my change in velocity. And that's the same direction that my acceleration will be in. So over here, my acceleration actually points in a direction like that. And the car was never actually moving in that direction at all. So once again, acceleration doesn't tell you exactly what's happening with your motion. It tells you how your motion is changing. And just to finish off, let's look at our pizza trip again. Let's drive our car, collect a pizza, and then drive back home again. Remember how that looked? We'll be a little bit more realistic this time than we were last time. We'll actually, on our position versus time graph here, we'll think about the fact that we don't start off instantly at some speed. We'll start off and we will actually speed up a bit. And then when we get to the pizza shop, we'll slow down and stop for a while to pick our pizza up. Then we'll have to speed up again until we start heading home. And then when we get home, we'll have to slow down again before we stop. What does that mean in terms of our velocity? Well, our velocity is certainly not constant here, but what's going to happen to it? Well, it's going to start off 0, and it's going to increase until we get to some constant value, until we get close to the pizza shop, and then we're going to start slowing down. So it'll come back down to 0, and it will stay at 0 while we're at the pizza shop. And then as we go to leave the pizza shop, we're going to have to speed up, but again in the opposite direction. So our velocity will now become negative. And again, it will get larger and larger to get to some constant negative value on the way home. And then as we get close to home, we will slow down again until we've stopped at home. Now remember, acceleration is the slope on a velocity versus time graph. So we can see here at the start of our journey, we actually had a positive acceleration. We were speeding up in the positive direction. When we reached a constant velocity, our acceleration was 0. We were moving, but we weren't changing how we were moving. Then when we got close to the shop, we had to slow down, and we had indeed a negative acceleration. Then when we stopped, we once again had 0 acceleration. Then when we started to go home, we had to speed up in the negative direction until we got to a constant velocity one more time. We're still moving, but no acceleration. And then as we slowed down to get home, we now actually have a positive acceleration because we're moving in the negative direction, but slowing down. Now, there's a lot of positives and negatives to keep track of in there, and it's really important you look at graphs like the one we've just drawn to make sure you understand how acceleration relates to velocity and how velocity relates to position, particularly the changes in those things. And keeping in mind the whole time, these are vector quantities. What we'll do in the next topic is use acceleration, velocity, and time to generate a bunch of equations, so-called equations of motion, that will allow us to calculate where things will be, how fast they'll be moving at various points in time.